We must first answer this question. What is CAE? With the advent of technology, the use of computers in solving problems and making various products has been expanded. Computer-aided design, analysis, and fabrications are divided into three parts: CAD, CAM, and CAE. CAD is abbreviated from computer-aided design. For example, CATIA and SolidWorks are dedicated for CAD usage. CAM is abbreviated from computer-aided manufacturing, such as CATIA and Procast software. CAE is abbreviated from computer-aided engineering, and for analysis, software like Abaqus and ANSYS, LS-DYNA, and COMSOL are being used. CAE, used exclusively in Abaqus, stands for Complete Abaqus Environment. CAE consists of three sections: pre-processing, processing, and post-processing. We will explain each of these three sections in following slides. We want to introduce the software environment window in full details. We see the menu bar, toolbar, and context bar at the top of the software screen. For example, in context bar, you can access modulus, models, and parts in drop-down menu. In the Model Tree section, you can give your model any changes you want before post-processing. In the Results Tree tab, you can also do tasks related to post-processing such as plot diagrams, generating report, and so on. The Toolbox area has different tools depending on each module. For example, you can see tools related to part modulus in the figure. Viewport is a window in which you can view your model. Prompt area is used when you use a tool in a module. You will see a description of it in this section. In the message area, you can see the messages that the software gives. And in the command line interface that is activated by passing this yellow button, you can do the scripting in Python or use calculator. For scripting, you can use our scripting packages presented in three levels: scripting for beginners, advanced levels, and writing plugin. Processing will include all things you need to do before you give your model to the Abaqus solver, including creating the model geometry, defining the material and assigning it to the model, assembling the model, and placing them in the right place. Selecting the appropriate solver in the step section according to the type of problem. Determining boundary conditions and loading an interaction between all parts of the model, meshing and assigning elements to the model. Note that you can create part in other software like CATIA and import it in Abaqus. Also, if your model is made, you can use its input file in other software. This means that there is always a connection between Abaqus software and other software in the processing stage. Well, for example, here you see a hinge with a pin on it. You can see in the figure all necessary actions that must be done in each module. For example, in the part module, our model must be designed or imported. In the property module, material must be created and assigned to sections. In the assembly environment, specify the position of the pin and the hinge relative to each other. In the step module, our step type must be defined, for example, dynamic or static. In the interaction module, the appropriate contact must be defined between the pin and the hinge. In the load section, we must define the boundary conditions, such as the fixing of the two sides of the hinge, as well as the capability of the pin rotation inside the hinge. And finally, in the mesh module, we have to do the meshing. This is a small part of the Abaqus for Beginners training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic in training so that you don't get tired of Abaqus errors. After our model is ready, we have to give the model to the software solver to solve it. And while the problem is solved, you can monitor the result, like the window you see here. Note that this window is for standard solver and is not the same as other solvers, the description of which will be provided later. Solvers can be of Abaqus Standard, Abaqus Explicit, and Abaqus CFD types, each of which has a different solution method. Once the simulation is completed, you can view the results in the post-processing section. You can even take action on the results and define new variables based on them. You can plot graphs of each result corresponding to each other. In addition, we can view the result in a specific element or node and even compare it with a laboratory result. An important issue in Abaqus software is applying units in Abaqus. Units are not specified in Abaqus and you must comply with the compatibility of the units. By specifying the unit of three quantities like mass, length, and time, the unit of the other quantities is determined based on their physical relation. For example, in the SI unit, which units weight and length and time are kilogram, meter, and second respectively. The stress unit is Pascal and the energy unit is Joule, and so on. The values provided for density and Young's modulus are for steel. For example, for kilograms, millimeters, and milliseconds, other units are determined according to this line. Force unit will be kilonewton, stress will be based on gigapascal, energy unit will be kilonewton millimeter, and density as follows. For more information, you can see the units in Abaqus article on the website. For example, here we have the unit of length and force as well as time if we have to determine the time-dependent problem. And considering them, we get the units of other quantities such as stress and density. In general, you only need to define 3 units and specify other items through them. If you were to use millimeters instead of meters per unit length, then the stress unit would be megapascals, and the density unit would be ton millimeters cubic. Through this link, you can access the complete description of the units. To start the simulation, we must first refer some points about it. First of all, each of your projects should be placed in a unique separated folder, because by default the software puts the simulation files in the temp path, and it may lead to missing data in the future. To do this, copy the address of your desired storage location, and after opening Abaqus and clicking on the File option, paste it in the Work Directory section. This is a small part of the Abaqus for Beginners training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic in training so that you don't get tired of Abaqus errors. In this section, we want to calculate the P number. As we calculated, the parametric size of each side of this polygon is equal to 2r multiplied sinus P divided to n. Now, if we want to find the perimeter of an n polygon, we need to multiply this value by n. Set the value equal to the circumference of the circle, which is 2 multiplied p multiplied r. After simplifying the equation, the p number becomes equal to the value shown here. By placing n with different numbers in the equation, p number becomes equal to the value shown here. We conclude that after the number 128, the value of p reaches approximately a constant value of 3.14. Let's take an example related to the simulation subject. Assume that the left side of the structure is fixed by these two holes and a force is applied to the bottom of right hole. And we want to calculate the amount of torque or a stress in section AA. To do this, we can simplify this problem to a cantilever beam. As a result, the moment and deflection values of the end of the beam are equal to the following formulas. Note that this is an estimate of the calculations of our original model, and the calculations for the original model are much more complex. And the answer may even differ depending on the presence of the items, such as the stress concentration in the hole and the place of support. Thus, we need an easier and practical method like the Finite Element Method, FEM, to solve this problem. So, in the FEM method, this structure is divided into smaller pieces called elements. Each element has its own element ID number, and in each vertex contains a node with a specific ID number. For example, this is an element with the ID number 3245 that has nodes with the ID numbers shown. How finite element works. First of all, our structure is divided into overlapping pieces, each of which is called an element. And each vertex of these elements is called a node. The second stage is that the behavior of each element will be formed. Its behavior is determined according to what type of element it is. Finally, it obtains the behavior of the whole structure by assembling the behavior of the all elements. There are different types of elements. Number 1, one-dimensional. Number 2, two-dimensional, such as triangular and rectangular element. Number 3, three-dimensional, such as pyramidal element and rectangular cube. All elements are connected by nodes, so some nodes are common. For example, here we have 3 elements that between elements 1 and 2, nodes 6 and 2 are common. The answer in element 1 is obtained by interpolating nodes 1, 2, 5, and 6. For example, suppose that we have displacement values in nodes 1, 2, 5, and 6. So, the displacement in the element will be equal to the interpolation of these nodes. The finite element can be used in various problems. For example, in problems that either do not have a test result or obtaining the results is so difficult, such as problems with very large structures, or problems from which test results can be extracted, such as mechanical problems or electrical problems. How does it work? To use FEM, governing equations and boundary conditions will become a definite equation. Our problem can be elastic, thermal, fluid, electrostatics, and so on. For each of these problems, or a combination of them, governing equations that include its differential equation and its boundary conditions should be specified to implement in FEM. In the following, I will explain what happened to these equations to solve problem, for instance, in a huge structure case. For example, we have vertical machining here. We want to study the behavior of the structure according to the movements in the structure in terms of stress, displacement, and other issues. As you can see, the problem has a complex geometry. In the first stage, governing equations and boundary conditions will become an equation. These governing equations cannot be directly analytically solved for a complex problem. So we turn it into a finite element problem to create a relationship shown here as K multiply U equal F. K is the property that can be different for various problems. For elastic problems, it is stiffness. For thermal problems, it is conductivity. For fluid problems, it is viscosity. The behavior of the material, which can be a degree of freedom. For the elastic problem, it is displacement. Temperature for the thermal problem. Velocity for fluid problems. Action can be force, heat source, or body force. The goal of finite element problems is to calculate U. It actually calculates the degree of freedom for each node. To calculate U, all you need is to solve the equation on the right side. Because governing equations are so difficult to solve, such a process must be followed. First, the whole structure will be divided into very small elements. Note that these elements can have different types of 3D, 1D, and 2D. These elements have common nodes with other adjacent elements. These nodes share their degree of freedom with the side element. Solving equations for each element is easier than solving governing equations for the whole structure. So the software solves the shown relation Ku equal F for each element. The variable K is different for each element. Then all the elements and boundary conditions are assembled together. And the relationship becomes the relation to the left, where K will be a combination of the material behavior of different elements. By solving this equation, we come to the right relation, which is to calculate the degrees of freedom for different nodes of the whole structure, and these calculations are performed by a computer. When U is obtained for the whole structure, U is also calculated for each element, and other fields such as stress and strain are also calculated by it. One of the advantages of finite element is that it can solve very complex problems. It can solve all kinds of engineering problems such as solid mechanics, dynamics, heat problems, and so on. It can model complex constraints, and it can also handle complex loads, such as loads in nodes or loads in elements. This load can be pressure, thermal, inertia, variable force, and so on. It can solve even problems that depend on time and frequency, or a combination of place and time. Disadvantages of finite element. It has no closed form solution. That means it does not have a definite relation that we can change its parameters to find answers to various problems. While in analytical method, the closed form solution is available. Second, the finite element gives us only an estimate of the answer. The inherent errors that finite element gives us and errors that may occur by the user, which will be further explained in the following slides. Inherent errors. No matter how small the elements are, the domain created does not match the main domain. We estimate the behavior of each element by a function. For example, in the beam element, if the actual behavior is in the form of the left diagram, its behavior by FEM can be linear, quadratic, or cubic. But even in the cubic case, which is still third degree, there is a difference with the main behavior. Third, for integral calculations of some parameters such as stiffness, we use simple methods such as quadrature Gauss, which gives an estimate of the answer to the problem and thus causes an error. This is a small part of the Abaqus for Beginners training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic in training so that you don't get tired of Abaqus errors. One of the inherent errors is that the calculations we use only a number of decimal places. For example, we can't put p in calculations and we have to use its engineering equivalent number. Numerical errors may also occur. Suppose that you have a structure with two springs, the stiffness of one of which is much larger than the other, in which case the displacement for the smaller stiffness goes to infinity. Errors that can be done by the user include selecting element incorrectly. For example, use shell element where solid element is needed. Another thing is that the points related to the generating of the element are not observed. For example, its size is not entered correctly, which causes distorted elements. Thirdly, defining incorrect boundary conditions by user in the problem and cause the movement of rigid members in the structure. Furthermore, the user will use incompatible units, for example, using gigapascal for E and pound for load. Lastly, using the stiffnesses that are so different from each other that was mentioned in the previous slide. An example of a FEM analysis is the analysis of a spring problem with hardness K, force F, and displacement X, which respectively K is property, F is boundary condition or loading, and X is the degree of freedom. The next topic in FEM is the degree of freedom. If we only have degrees of freedom of movement, U, 3 degrees of them is the translation, and 3 degrees of freedom is rotation. If we want to model a real problem that is 3-dimensional in 1 dimension or 2 dimensions, it can be one of the modes of axisymmetric, plane stress, plane strain, shell, and membrane. The feature of plane stress is that the size of one of the dimensions is very small compared to the other dimensions, and the stress is inside the plane, in which case the use of the plane stress element is correct. 2 features of this element are that the stresses on the plate have a constant value in the thickness direction. Second, the stress in the thickness direction is 0. In the plane strain element, unlike the plane stress element, the size of one dimension is much larger than the other dimensions. In this case, we can say that the strain occurs only inside the plane, and we will not have a strain in the Z direction. In convergence, the problem must be solved regardless of the numbers of elements. That is, we have to solve the problem with different number of elements, and the difference in answers should be less than 10%. In this case, we can consider convergence study is done and the final answer is correct.